All right, welcome everybody. Today we're going to talk about Calc Lesson number 41. This is our third day of optimization, and the theme is finding the area of a rectangle under an equation and finding the shortest distance from an equation to a point. So kind of a mouthful. Some of these problems might seem unfamiliar at first, but hopefully after we do a few, you'll find they're very similar to days 1 and day 2, at least in terms of how you're going to approach the final answer. So just something to note here, these are the same problems that you have on your worksheet, although I've blown them up a little bit bigger so you could see them. Secondly, you just might want to write small or consider using a separate sheet of paper since we put all 5 problems on one sheet to save paper, but you just might need a little bit more room. So here in number 1, a rectangle is bounded by the x and y axis and the graph of y equals 3 minus 1/2 x. So if you look at the picture that's given here, you of course have your x-axis, then you have your y-axis, and then we've gone ahead and drawn for you the line y equals 3 minus 1/2 x. You would, of course, start at a y-intercept of 3, go down 1, right 2, a couple different times until you intersect the x-axis. So what length and what width should the rectangle have so that its area is a maximum? So we are looking first and foremost for a length and a width, and we of course would like that area to be a maximum. So area is the formula that we are ultimately going to need here. Just to be clear, the rectangle that is shown in the picture, we're not saying that that is the winning answer. We're just saying that's one possible answer. So you don't necessarily have to write this down, but all the different possible rectangles that could exist, all we know is that it has to be bounded by each of the axes and the line. So we could have this rectangle here. We could have this rectangle here. We could have this rectangle here. There are lots of different possibilities. So the one that's drawn for you there is just kind of showing you, a potential solution. The whole point of this problem is you, of course, actually want to find it. So if we're going to go about doing that, a couple things to get us started. When we're talking about the length and the width, let's go ahead and call the length x, and we're going to call the width y. So that means that from left to right is going to be our x distance, and then from bottom to top is going to be the y distance. Something that we want to consider here, and something that you want to consider for a lot of problems like this, where you're trying to find the area of some shape bounded by a curve, you want to consider the domain of x. If you're looking at what's happening here, because it has to be bounded by the positive y-axis, the positive x-axis, and the line y equals 3 minus 1/2 x, the smallest that x could possibly be would be if it was on the y-axis, which means it would have a value of 0. And the largest that x could possibly be would be if it was the x-intercept of the line, because you obviously, anything farther than that would go into the negative region. So the domain of x is telling you that you can only have values between 0 and 6. So that's just something good to keep in mind in terms of making sure that your final answer actually makes sense. Just a quick note about why the domain is parentheses as opposed to being brackets. If you were actually at x equals 0, or if you were actually at x equals 6, you would have y values of 0, which means you wouldn't actually have a rectangle at all, which is why we have to use parentheses as opposed to using brackets. Because of the fact that we are trying to maximize area, we of course have to remember that the area of a rectangle would be length times width. So we're going to go ahead and call that x times y. Just as we've seen before, we need to have one variable, most commonly x. So if area equals x times y, luckily for us, we know that y is equal to 3 minus 1/2 x. So we're going to go ahead and make that substitution, and we're going to plug that entire value in for the y. That's going to give us a new area equation of x times 3 minus 1/2 x. We're going to go ahead and distribute. So the area is 3x minus 1/2 x squared. So again, that is the area formula for a rectangle that potentially is bounded by those 3 curves, and we are trying to maximize it. Well, as we've seen the first 2 days, if you are trying to maximize or minimize something, it means you're going to take the derivative. So the derivative of a would, of course, be a prime. That would be 3 minus, bring down the 2 times 1/2 is just 1, and then x to the 1 less power. Once you actually find the derivative, if you're trying to maximize or minimize, that means where the slope of the tangent line is equal to 0. So we're going to go ahead and set that equal to 0, which means that x is going to be equal to 3. That may or may not be your answer. You have to make sure that you read the question carefully and make sure that what you have either is an answer or you might need to find the rest of the answer. So they asked us here, what is the length and the width? So the fact that we solved for x equals 3, that is part of our answer. That is the length. And now to find the width, you have to go back to the fact that y equals 3 minus 1/2 x. So y equals 3 minus 1/2 times 3. So y equals 3 minus 1.5, which means y equals 1.5, and that's going to go ahead and give you the width. So let's just go ahead and highlight them there. So 3 and 1.5. So again, if you go back to the picture in question here, they're telling you that x should be exactly 3 and y should be exactly 1.5. So based on the picture that you see here, you can see that you actually want your rectangle to be a little higher on the y and a little smaller on the x. You don't have to actually draw that rectangle in, but again, the rectangle that's given to you is just one potential answer. You won't know for sure what the right one is until you kind of complete the entire process. So let's go ahead and take a look at number 2. There are similarities, but there are also differences as well. So here you have rectangle ABCD. The sides are parallel to the coordinate axes, and it is inscribed in the region, which is enclosed by the graph of y equals negative 4x squared plus 4, which is shown for you in the figure. Find the x and y coordinates of the point C. So the area of the rectangle is a maximum. So they're telling you to find the x and y coordinates of the point C. So that means at point C, we know that there is some point x comma y, and that's ultimately what we're looking for. So your final answer should be an ordered pair x comma y. So again, as always, just make sure that you answer the question in its entirety. So a couple things we have to watch out for here. Compared to number 1, the reason why this is different is because we have part of our rectangle on the right side of the y-axis, and then we have some of our rectangle on the left side of the x-axis. Now, normally when you graph things to the right, they're positive, and when you graph things to the left, they're negative. Because of the fact that we're talking about an area, we're really kind of talking about a distance for the length and a distance for the y. So when I go to set up my variables, I want to make my height y, but then for my length, I want to make this a value of x, and I want to make this a value of x. Now, again, the reason why you can't make the whole thing x is because a positive value and a negative value would essentially cancel each other out. If you're just talking about distance, the fact that the left side would be negative really wouldn't matter. We're just looking for the distance. So we're going to make both sides equal to x, which hopefully makes sense then that the entire distance of the length from left to right should be 2x. So because of the fact that we are trying to maximize the area, that means that I'm going to have to do length times width. And in this case, based on the variables that I have assigned, I'm going to say that the area is equal to 2x times y. So that's the area equation that I'm going to use. Again, something that you might want to find here, you know that this is an example of negative 4x squared plus 4. In terms of your potential answers, you might want to consider the domain. So if you go ahead and set that equal to 0, and then you solve for the x's, you're going to get 4x squared equals 4, which means that x squared equals 1, which means that x equals plus or minus 1. The reason why that is useful, so this is the point negative 1 comma 0, and this is the point 1 comma 0. So that's just useful in terms of the domain. So if we're looking for the domain of x, it has to be between 0 and 1. And again, even though there's an x on the left side as well, because we're just talking about distance, we're talking about positive possibilities, which means there's no way that the right-hand side could go farther than the x-intercept over there at 1. So taking a look at everything I have so far, because of the fact that I am trying to maximize my area, 2x times y, just like before, we want to go ahead and rewrite that using a single variable. So area equals 2x times negative 4x squared plus 4. Now, of course, we're going to go ahead and distribute. So negative 8x cubed plus 8x. Now that we have our formula for area, we're going to go ahead, of course, and take the derivative. So a prime would be equal to negative 24x squared plus 8. We're then going to go ahead and set that equal to 0. So 24x squared would be equal to 8, which means that x squared would be equal to, careful, 1/3 if you divide by 24. Then you're going to go ahead and take the square root. So when you take the square root, you're going to get plus or minus. The square root of 1/3 is the square root of 1 over the square root of 3, which if you rationalize is plus or minus radical 3 over 3. Because of the fact that, again, we're saying that x has to be some positive distance, we're going to go ahead and say that x is equal to root 3 over 3. We're going to need that. Again, that's not our final answer, but it is something that we want to keep in mind. So going back to the original problem, remember they wanted us to actually find the coordinate of point C, x comma y. So we have found the x coordinate. Now we have to find the y coordinate. So to find that y coordinate, you're going to take that x and you're going to substitute it back into the y equals negative 4x squared plus 4. So y equals negative 4 times the square root of 3 over 3 squared plus 4. Y equals negative 4. The square root of 3 squared is 3. The regular 3 squared is 9. So 3 over 9, that is, of course, equal to 1/3. 1/3 times negative 4 would be negative 4/3. And then instead of saying plus 4, we're going to say plus 4 over 1. We're going to find a common denominator, which would be 12/3, which means that y is equal to 8/3. And again, because they asked you for the actual coordinate, you have everything you need. You just have to make sure you understand that the coordinate of point C is equal to the square root of 3 over 3, comma 8/3. So that is ultimately the final answer that you want, again, some ordered pair. And then just to point out how that makes sense, if you go back to the original picture, the fact that you're looking for point C, that's over there in the first quadrant, which means it should be positive, positive. Again, if I had asked you for point B or some other value, then you would have answered the question differently. But because I'm asking you for point C, it's the square root of 3 over 3, 8/3. And if you check the value of the square root of 3 over 3, I promise you that it is, in fact, less than 1. So everything makes sense, again, in terms of a domain perspective. All right, so take a look here at number 3. And the truth is, I have made an executive decision that we're going to actually go ahead and skip number 3. I'm going to just kind of talk to you about the setup, but we're not actually going to finish it all the way through. The reason being, because of the fact that this is a semicircle, it has a square root, which means we're going to need the chain rule and the product rule and that fancy factoring. And really, we're kind of focusing more on just the general optimization techniques. And we don't really want to go back to that really difficult algebra. But just to kind of talk about the setup, you have a similar scenario to the previous problem. You would be looking for the length and the width that would give the rectangle drawn have an area of a maximum. So again, to kind of point out a couple of things here, if you were going to give it some variables, you would again have to call both distances x because of the fact that a distance essentially needs to be positive. That would make the entire left to right be 2x. That would make you have a height of y. You would take this square root function and set it equal to 0. Then you would square both sides, put them on opposite sides, and get x equals plus or minus 5. That's how you know that these would be the x-intercepts of the semicircle, which means your domain for the x would only be between 0 and 5. And then again, to finish it, you would go ahead and write an area equation. You would then find the area by multiplying x times y, and that would give you x times the square root of 25 minus x squared. And then that's where things would kind of start to be difficult. You'd have to rewrite that square root as a 1/2 power. You would then have to do the product rule and the chain rule. And again, because of what we're really trying to focus on here, we don't actually want to follow it all the way through. So as long as you understand the setup, I'm going to go ahead and consider that a win. So even though we skipped number 3, everything about the first 2 problems was talking about maximizing some area that was bounded by a curve in the coordinate plane. These last 2 problems have to do with distance. So you might want to start by reminding yourself of the distance formula. You're going to need that. So the distance formula, and we call that d, is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And of course, everything should be under the radical. So again, you might just want to write that down so that you have it for easy reference. So now let's take a look at what it is we're actually being asked to find here. So determine the point on the line y equals 2x plus 3. So the distance between the line and the point 1, 2 is a minimum. So now we're trying to minimize something as opposed to maximizing something. But again, the derivative is what's going to allow us to do so. So notice, of course, that I started by graphing the line y equals 2x plus 3, and I graphed the point 1, 2. So since we didn't graph that for you ahead of time, you might want to go ahead and jot that down on your paper. And of course, the line y equals 2x plus 3 has a y-intercept of 3. You would go up 2 over 1 or down to left 1 a couple of different times. Again, really keep in mind what it is they're asking you for. They are asking you for a point. So they're looking for an ordered pair, x comma y. It has to be on the line, y equals 2x plus 3. And you want the distance between that point and 1, 2 to be a minimum. So again, think about what that's saying. They're saying that there's a point on the line, x, y, and it could be this one. Or it could be this one, or it could be this one, it could be this one, it could be literally any point on the line. We don't know which one it is. That's exactly what it is we're trying to calculate. So we're just going to choose any random point on the line to start. And so we're going to call that point xy. And then, of course, we have the ordered pair, 1, 2, and we are trying to minimize the distance between them. So if we're trying to minimize the distance, we're going to go ahead and start with a fresh copy of the distance formula. So again, rewrite that one more time. So x2 minus x1 squared plus y2 minus y1 squared. So let me assign some variables here. I'm going to go ahead and make the point 1, 2 my x1, y1, and then I'm going to make this x2, y2. It doesn't matter which you make which, but this is actually going to wind up being a little bit nicer. So I'm going to go ahead and start by plugging in the x1 and the y1. So this is going to give me the square root of x2 minus 1 squared plus y2 minus 2 squared. Then I have some additional substitutions to make. Remember, I want to be down to just one variable. So because of the fact that I called my x2 for my x, I can go ahead and just replace x2 with x minus 1 squared. And then my y2 is equal to y, but I don't want there to be another variable. So luckily, because of the fact that y is equal to 2x plus 3, I can go ahead and make that substitution. So I'm now going to say 2x plus 3 minus 2 squared. Again, you might want to use a separate sheet of paper. You might run out of room. There's kind of a lot of steps here. So to kind of keep going, this is going to be x minus 1 squared plus, this is 2x plus 1 squared. Now I have to do both of those FOILs underneath the radical. So x minus 1 squared, that's going to be x squared minus 2x plus 1 plus 4x squared plus 4x plus 1. I think at this point in your mathematical careers, you should be able to do those FOILs in your head, but if you need to write out all the steps, that would be fine. So d is equal to the square root of, if you go ahead and combine all the squareds, you get 5x squared. If you combine all the x's, you get 2x. And if you combine all the constants, you get 2. So this is, in fact, our distance formula, of which we are trying to minimize, which means we're going to have to go ahead and take the derivative. So if I'm going to go ahead and take the derivative, the first thing that I'm going to want to do is I'm going to want to just rewrite that as a 1/2 power. So this is going to be 5x squared plus 2x plus 2 to the 1/2 power. I'm going to now go ahead and find the derivative. So I'm going to bring down the 1/2. I'm going to then take the entire quantity to the 1 less power. Then I need to do the chain rule. So the chain rule is the derivative of the inside, which would be 10x plus 2. So I know we skipped the previous problem because it needed the product rule and the chain rule, but here we just need the chain rule. So we're going to go ahead and find it all the way through. So to clean things up just a touch, I'm going to take this 1/2 and I'm going to take this 10x plus 2, and I'm going to go ahead and just combine those together. So I'm going to get d prime is equal to, and then 10x plus 2 times 1/2, that's 5x plus 1 over 5x squared plus 2x plus 2 to the 1/2 power. So now there's again a little bit of a throwback here, but it is worth doing. So now that I have a numerator and I have a denominator, you're going to have to think back to earlier in chapter 3. When I set this bad boy equal to 0, I am going to have to find the critical values. The critical values meaning things that make the numerator 0 or things that make the denominator 0. So I'm going to have to go ahead and set each of those equal to 0 and then solve. So if I set the numerator equal to 0, 5x plus 1 equal to 0, I'm going to go ahead and get x equals negative 1/5. If I set the denominator equal to 0, the 1/2 would essentially go away by squaring both sides. And then in order to solve what's inside, I could try to factor it, but it won't. So I would need to do the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac. And right from there, I can actually stop without even actually writing anything else. The reason being is that underneath the radical is a negative, which means this is going to yield an imaginary number. An imaginary number can obviously not be a solution. So the fact that there are only imaginary solutions means that there are no critical values from the denominator, which means that I can't find any values there. So while that was annoying to have to use the quadratic formula, there is good news. If the only critical value is negative 1/5, then that means that that does in fact have to be the answer. So x equals negative 1/5. And then again, as always, go back and just make sure you've answered the question. The question is, you want to find the point x comma y. So all you've done so far is find the x value of the coordinate, negative 1/5. You're now going to have to find the y value of the coordinate. And to do that, you're going to plug into y equals 2x plus 3. So y equals 2 times negative 1/5 plus 3. So y equals negative 2/5. And then instead of 3, I'm going to say 3 over 1, which is, of course, 15/5, which means that y has to equal 13/5, which means that is the value of the coordinate pair that has a minimum distance from the point on that line to the point 1, 2. So a lot of times these answers wind up being some kind of radical or fraction or decimal. So don't be surprised if that happens. Also, it does often happen that you wind up with one of these situations where the quadratic yields an imaginary solution, but you do have to check for sure. And again, -1/5, comma 13/5. Where would that point live? Well, it turns out my estimation was somewhat close. But again, you don't have to actually draw it in. You just have to know that that is in fact the answer. So one final problem to finish us off. It's very similar in terms of distance, but it's actually going to be a little bit easier. So you're welcome. Here we have the graph, the square root of x, which I've drawn for you there, which you might want to draw on your paper. Hopefully you remember that's the scoop. It starts at 0, 0. It goes through 1, 1, 4, 2, 9, 3. You're trying to find the point on the graph that is the closest to the point 7, comma 0. So just so you're aware, when you see the word closest, that is again asking for the minimum distance. So please make sure you know that that's asking you the same thing. And again, they are asking you for the point, which means your final answer has to be a point x, comma y. So just make sure you've answered the problem in its entirety. They are asking for you to be a minimum distance from the point 7, comma 0. So you'll notice I have given that to you as well. And then again, there are so many points that could be the answer. This could be the answer. This could be the answer. This could be the answer. We don't actually know which one is which. So we're going to go ahead and just draw one at random. We'll draw that a little nicer for you. We're going to go ahead and just select one at random. Remember, the whole point is you're actually trying to solve for it. So we're looking for that minimum distance D, and we are looking for some point on the graph, x, comma y. Again, because this is a distance situation, let me go ahead and start with a fresh copy, given as such. Again, you're going to go ahead and label the points 1, x1, y1 and 1, x2, y2. It doesn't matter which is which, but it is generally easier if you make the number x1, y1 and then x2, y2. So I'm going to go ahead and start by plugging in just my numbers. So x2 minus 7 squared plus y2 minus 0 squared. Then I'm going to go ahead and sub in x2. So x2 is really just x minus 7 squared. And then y2 is really just y, but I don't want it to be just y. I would like it instead to be an x. So I'm going to go ahead and sub in the square root of x minus 0 squared. So go ahead and FOIL. X minus 7 squared gives me x squared minus 14x plus 49. Plus, the second parentheses is nice because the square root of x minus 0 is just the square root of x. And if you square the square root of x, you actually just get x. So that means that my distance is going to be x squared minus 13x plus 49. And instead of writing that as a square root, I'm just going to go ahead and write it to the 1/2 power. So now derivative time. So d prime is equal to, again, bring down the 1/2. That's going to give you x squared minus 13x plus 49 to the 1 less power. Then don't forget the chain rule. And the chain rule would be 2x minus 13. So from here, you're going to go ahead and rewrite it. So you're going to go ahead, well, set it equal to 0. Then you're going to go ahead and rewrite it. So in the previous problem, this 1/2 and this value that was here had multiplied out to be nice numbers. Here, they're going to wind up being decimals, but you can still do it if you want to. So 1/2 of 2x would be x, and then 1/2 of 13 would be 6.5. Or let's actually say 13 halves. And then in your denominator, you would have x squared minus 13x plus 49 to the 1/2 power. And then again, because of the fraction action, you would have to find the critical values. The critical values would first come from setting the numerator equal to 0. And if you set the numerator equal to 0, you get 13/2. Then the second set of critical values would potentially come from setting the denominator equal to 0. Again, you should for yourself double check on the homework, but I can tell you I've already done it, and they do in fact wind up being imaginary. What that means is that there are no critical values from the denominator, which means the one from the top has to be the answer. But again, that's only half the answer. They asked you not just for x, they asked you for x comma y. So in order to find the corresponding y value, you're going to go ahead and take y equals the square root of x. And you're going to substitute in 13/2. So you get the square root of 13/2, which becomes the square root of 13 over the square root of 2, which you'll then rationalize to be the square root of 26 over 2. And again, that's because you multiplied by root 2 over root 2. So here's my x and here's my y. And if you just want to be, super fancy, you're going to go ahead and write that as 13 over 2, comma, the square root of 26 over 2. So clearly a lot going on here. Again, I would focus mostly on two different types of problems for today. The first two, making sure you could set up an area formula, making sure you're making the distances all positive, and then maximizing the areas. Then for these last two problems, you're trying to find the minimum distance. So again, you're going to need to use the distance formula, and you're going to need to use the chain rule, and watch out for those imaginary answers. So for the homework, we focused on quality over quantity. So hopefully you find it manageable. And thanks very much for tuning in, guys, and we will catch you next time.